Okay, let's go. So yeah, we left off kind of in the middle of something last time, so I kind of want to finish that. So yeah, we're going to continue with 5.1. This talks about the integral and approximating areas. So last time I had approximate the area under the graph. It was, I think it was f of x equals x squared plus 1. On the interval was 0, 1, 5.
Yeah. Using 4 subintervals and right-hand points.
Using 4 subintervals and 8 right-hand endpoints. And this one we actually did.
Yeah.
So now I want to show you how to do things with the left hand, which is very similar to the right hand. It just depends on the side of it. And also the midpoint. So let's do B. Okay, so we're given the function, we are given the interval. And so one of the first things we want to find out, remember, it's the spacing. So we are on this interval, 1 to 5. I know I need to cut it into 4. With these numbers, it's obvious what the guys should be, but if these numbers are weird, then you just use the fact that you remember that delta x is equal to b minus a over n. N is the number of subintervals or the number of rectangles. And B is the final endpoint, so that would be your B. A is always the initial endpoint, that's the A. Right? So in this case, I know my delta x would be 5 minus 1 over 4, which was 1 in this case. And so that means the spacing here is of length 1. So if I start at 1 here, that would have to be 2, this would have to be 3, this would have to be 4. And so now, because I'm in the left-hand endpoints, what am I going to do? I'm going to look at each interval, and what am I going to pick?
The left-hand side?
The guy that's on the left. So on this interval, I would choose the number 1. On this interval, I would choose the number 2. On this interval, I would choose the number 3. And on this interval, I would choose the number 4. So this means that my area is roughly equal to the left-hand endpoint at 4, which is just going to be delta x times f of these values. F of 1, f of 2, f of 3, f of 4. Right? Notice that the only difference between this and the right-hand rule was the numbers that I plugged in. I plugged in the numbers that were on the right hand, right? So when I was doing the right-hand endpoints, I tried 2, 3, 4, and 5. Now I'm on the left, I'm going to try 1, 2, 3, 4, right? Because those are all the guys on the left. 5 is obviously left out because it's on the right side of the interval. And so at this point, delta x is just 1. And right now I'm just plugging in these answers into the original function. So that's going to be 1 squared plus 1 plus 2 squared plus 1 plus 3 squared plus 1 plus 4 squared plus 1. Which is, again, 1 plus 1 plus 1 plus 1 was 4 plus 1 plus 4 plus 9 plus 16. Okay, so 9 plus 16 is 25, plus 5 is 30, that's 34, right? Yep. So that's my approximation for the area according to the left-hand endpoints. Notice that it is smaller than the right-hand endpoints. The reason for that being, You don't have to draw the graph unless you're specifically asked to draw the graph, but I know my thing will look like this. Because it's my left side that's touching the endpoints, these are what my rectangles will look like. So notice that they will give me a smaller value than the actual answer. Whereas in the case of the right hand, it was the opposite. They were above this curve, so they should give me a bigger answer. But that's it. Any questions? Okay. Now, I have to like hide the erasing. See?
I mean, we know what the triggers are. Aren't they in the same class? Doing 25?
Ooh. Over there? No. They're in probability. Using midpoints. This is the more complicated of all three methods, but it's still not that bad. All you're going to do now is you're going to take the middle points as the points you evaluate. That's basically it. So you start out, you know that you're on the interval 1 to 5, so you can draw this 1 to 5. You know you're going to cut it into 4 subintervals. You're going to find that your delta x is equal to 5 minus 1 over 4, which is 1. So you know that this is 2, 3, 4. And then what you're going to do is you're just going to take the middle value here, right? So let's look at this first point. How would I find the value that's right in the middle?
The average of...
The average, right? So to get my first point, I'm going to find the average of 1 and 2. This is just going to be 1 plus 2 over 2, which is 1.5, right? It's clear here. Or I can write that as 3 over 2, either way. Now once you do that, to jump to the next middle point, you're still adding a delta x, right? So it's 1.5 plus 1 gives you 2.5, plus 1 gives you 3.5, plus 1 gives you 4.5, right? So now these are the numbers that I'm going to be plugging into my function.
Will it always be that nice? Like the numbers look that nice where they jump pretty consistently?
The numbers always jump consistently. They'll always jump by this, but they won't always jump by 1. You could have a fraction or something like that, right? But you'll always jump by the same amount. And after that, the setup is just going to be pretty much the same. So right here, I'm going to say the area is approximately equal to the midpoint evaluated at 4 points. That's going to be delta x times f of 1.5 plus f of 2.5 plus f of 3.5 plus f of 4.5. 1 times 1.5 squared plus 1 plus 2.5 squared plus 1 plus 3.5 squared plus 1 plus 4.5 squared plus 1. You could do something like 4 plus 1.5 squared plus 2.5 squared plus. And sometimes you'll be asked, you can leave your answer as a sum of terms or a sum of fractions or whatever, in which case you just stop it. Because we do have a calculator, so you have to do that. And if the problem said leave your answer as a sum of fractions or something like that, you would instead write it in this form. Right? 1.5 is actually just 3 over 2. Right? And then 5 over 2. And then 7 over 2. And then 9 over 2. That's it. That's all there is to it. Questions?
Are we going to do another one?
Do another one.
Like this?
Okay. Which one do you want to do? We have three methods that we just considered.
We want all of them.
You want to do all of them again?
Yeah, we don't
Yes.
trust you. We don't trust you, so we need to see a lot of things.
What about one with like just a really ugly number?
What?
What would you give us? What would you give us on the final?
Fraction.
Um, okay. You want me to give you a really mean one?
No.
Like super mean?
Well, as long as it would be
Like what I give on a test, like?
Yeah.
Yes.
Okay.
You would really do us like that?
Yeah, let's do a super mean example. You're right. That was way too easy. I'd never ask you guys something like that.
No.
I'm so conflicted.
Minus x squared. Can't like distribute stuff, man. Okay. Let's make it really, really nasty. Okay, let's see.
You're having fun. I see it on your face. You know you're not looking to start.
No nasty, right? Six.
But you would never give us an integral as a fraction?
No. Like why?
Why would you ask for that?
Like, you can't trust me. Yeah, we.
Interval 1/6 with okay, really mean. Let's do 5 rectangles. And right hand being 4. And now we all panic.
Yeah.
Okay.
Okay, so what happens here?
Draw your number.
Line, 1, 2, 6.
Okay, so minus
5 rectangles, so cut up into 5 pieces.
so.
Then
Your delta t equal b minus a over n. Delta x, sorry. So that'd be 6 minus 1 over 5.
yeah, that's too nice, isn't it? Even when I try to be mean. Okay, 5.
Pi to the e.
Pi. Yeah, that's a nice one. Could do that. Pi.
Please don't.
Oh my god, it's a fraction. What do we do? I don't know about fractions.
So I had about 4/5. You skipped it.
Next
Oh,
one.
but yeah, but see now that's crazy. Because what the hell is 1 plus 4/5? I don't know that.
1 and 4/5.
9/5.
Are you guys sure? I don't know. I panic here. I don't know what. What would the next one be?
14.
Hmm?
14.
Wow, you guys are really good at this. What's the next one?
Isn't it?
No, what's that?
And then
Oh,
what?
it's not 44?
It's 5 rectangles.
This cannot be really
Um,
good.
Okay, so now what? Okay, now I'm stuck.
No. 24
You
over
doing
fifths
right,
plus 4 over fifths is not equal 6. Because
How about we
6
just stick to the one?
Mm-hmm.
Just give.
No, keep going, keep going.
It is going to be a test.
What did you guys add to the to get to this? Why did you add 5 to the 9?
He said
You
add
had-
one. You said add one.
You had one, so five.
Why were we adding
First,
one?
I'm bugging you. I'm bugging you.
You said what?
You see, I don't even have to try hard.
Wait,
So
what?
what?
Jhevon.
It's 4 fifths. Like, just added one. You just added 5 to everything. But we supposed to be adding 4 to everything.
I know it. Oh my god.
Something like this, Omar will be like, man, I can't even trust Jhevon, man.
You can't trust me.
I mean, in class, like, nope. Alright, so it's 13.
You should be adding 4/5 each time.
Yeah, it's 13.
So you're pretty much adding 4 to the top
Yeah,
each
so
time.
it's just 13.
So you add 4 plus 9, that's 13.
13.
Add 4, 17. Add 4, 21.
25. Or 5.
That should be 5.
And that makes sense.
No, but then that doesn't. Oh, never.
Yeah, you add 4 to that, you get 25 over 5, which is 5. Yeah, this is the guy you keep adding, right? So you start at a keep adding 4/5. Okay, after we do that, now what?
You just plug in those sub-intervals into your original function.
Plug in what cell into
Oh, yeah, the midpoints.
Right inside. So everything but the one.
Everything except the one I'm going to plug in. So my area is going to be approximately equal to R5, which is delta x times f of all the things on the right. You ignore the left endpoint. F of 9 over 5 plus f of 13 over 5 plus f of 17 over 5 plus f of 21 over 5 plus f of 5. Delta x is 4 over 5 times 4 minus 9 over 5 squared plus 4 minus 13 over 5 squared plus 4 minus 17 over 5 squared plus 4 minus 21 over 5 squared plus 4 minus 5 squared. And that's it. Yeah, that's the hardest I could make it.
So it'll be nothing harder than this right here. That's cool.
Nice cut.
It's not gonna be one whole question though. This would be like part A of a problem.
Oh,
I
no.
knew it. I knew it. Can't trust them. Can't trust them. Can't trust them.
Come on! I can't give you 20 points for doing that. Come on!
That would be very
No.
nice. We need it, yes.
Like in all the finals, this was like part A of something or part B
So
of
what's
something.
part B?
So at a for what topics we're covering? Wait, this is even in the. This would be under test 4.
Yeah.
So yeah, this would be a whole draw unto itself. Like there would be nothing.
20 points.
Yeah.
Really? This is 20 points, right here.
For test 4, it'll probably be worth 25. I think they're
Really?
4 probably.
One gets 30.
No, don't push it, because then you're gonna make it extra hard. And if you can't get it, that's 30 points. You're gonna set yourself down to 70.
Yeah, that's it. The worst thing you're gonna see is like your delta x is a fraction, and you have to remember how to add fractions, which I'm going to see.
Oh my God.
Let's make that mistake again.
Unless you make that mistake.
That's what
Right, you don't keep adding 1, you keep adding 4/5. Don't let the numbers scare you.
And the fraction will always be positive.
Oh yeah, would it be ever negative?
No,
How
it's
would you
a
have
distance.
negative
Oh yeah, yeah,
It's a
yeah,
length.
Yeah, yeah.
So it's always going to be positive. Yeah, that's it. Okay, so that's how I showed you how to approximate something. this is a whole problem to itself. Something else I might ask you is like in part B, is it an overestimate or an underestimate? Right, which in the previous example, right, so this is a whole question to itself. Part B might say, is this an overestimate or an underestimate? Overestimate means it's bigger than the actual answer. Underestimate means it's smaller than the actual answer. How do you figure that out?
Well, if it's asking for the right number, doesn't it automatically then?
Nope.
Do we have to draw the graph?
Drawing the graph would be a good way to do it. How do you draw 4 minus x squared? It's going all the way back to 3 go.
Parabola all the way to
It's an upside down parabola.
Yeah.
Right?
That,
Like that.
whose vertex is at 4.
yeah, not at the line.
And the right, it's at 4. I'll need more space here. Well, this problem is kind of unfair because it's there are negatives here. But with the previous example, the nice one, we could have done it nice. Because this would be like that. Right, because this would go through what? Like 2, right? So your 5 would be over here. And so what were our, we started at 1, and we wanted to go 9 over 5, and 13 over 5, and 17 over 5, more space, 21 over 5. And so we're taking the right hand. So we have this. And this one would actually go touch the curve. This touch the curve. This touch the curve. This touch the curve.
Why are we so like why is it upside down?
Because it has to touch the curve.
It touches the curve.
Is there any particular reason? Because the other one didn't. I mean, it touched the curve, but it was above.
No, you always touch. Yeah, because the function I gave you would happen to be on top the whole time.
We did it with the negative.
It's positive or negative.
Wasn't the question the area under the curve?
Mm-hmm.
I don't think over the curve.
Well, it's technically under.
Yeah, which is, I was going to mention something about that. It's really a net area. Like when your curve is under the x-axis, you actually get the negative of the area between the x-axis and that curve. So area under the curve is kind of area between the curve and the x-axis.
I don't get
Is
it.
it considered an underestimate then?
It's over.
I think there's more negative area than there is positive area.
It's
There's more negative areas than positive areas, right? So
It's over.
it would, technically here it would be under
Because it's negative.
because it's more negative. It'll give you a smaller answer than the actual curve would give you because it's going below the curve in the negative direction.
I don't want to see it. I don't get it.
Consistent color.
Well, you guys maybe give me a hard problem. Like I wouldn't ask something like that.
Conceptual.
It's like
Trust issues.
Right? Like look at consider this, right? Let's say what I'm really asking you to approximate is this area, right? That's what I'm asking you to approximate. Right? So let's say that gives you a number, right? So this would give you, I don't know, 2, and then this would give you a minus 3. Right? Whatever. Right? Then over here, because the negatives actually go below, right? This will give you a bigger negative area, right? So this is minus 3, this could be like a minus 5 instead, right? And this would actually give you less than the actual area here, right? So that could be like 1, right? So when I add these guys, right? This overall gives you the net area equals minus 1, right? Where over here, the net area would be what? -4. This is smaller. So it's an underestimate. Under means you're smaller.
So we have to compare, in order to answer B, we would have to compare.
You'd have to compare what the actual answer would look like to what the approximation would look like.
Okay.
Can I ask one more
Yeah.
example? If you were to have an S curve in a positive y direction, but all in positive x.
An S
Yeah, like increase and
Like
then
that?
like that.
okay.
Aren't you gonna get something that's harder to tell if it's a overestimate or underestimate?
Yeah.
But you wouldn't give us that, right?
No.
Okay.
And I wouldn't ask that question with a function like that. Right? So I'll ask one where it's obvious, like if the function is increasing, you know that a right-hand endpoint will give you bigger things, right? It should be obvious, right? Or if I ask you about the same kind of curve, if it's increasing, but I ask you about left-hand, it will give you something smaller, right? Whereas if I have a function that's decreasing and ask you about right-hand, that will give you something smaller, right? But if I ask you left-hand, that actually gives you something bigger. That's not. This topic in particular is not meant to be this crazy hard topic. It's kind of something that they want you to learn in passing. Right? It's of less importance than the derivatives by definition thing. Right? They torture you with that for a while, but afterwards you never use that. You just use the formulas. Okay. So, in theory, I don't remember if I mentioned this before. I feel like I mentioned it, but I'm not sure if I wrote it down. If we use an infinite number of rectangles, we can find the exact area under the curve. The idea is, the more rectangles I use, the more space I will fill in.
Yeah.
And with an infinite amount, I can fill in all the spaces, right? There should be no gaps. Right, and under is in quotations because, like I said, it's net area, right? So we're going to talk about, I'm going to mention that eventually, about how we think of area.
The actual remotes.
Okay, so this is going to be like an infinite Riemann sum. So, in other words, we would get the area is actually equal to, what you do is you start by what we had before, right? So you have delta x times, let's say f of x1 plus f of x2 plus f of xn, right? Where n is just the number of subintervals you're cutting something up into. But basically now you want to say that I want there to be an infinite number of rectangles. So basically all you do is just hit limit as n goes to infinity. You guys remember limits, right?
No.
That's it. Yeah, that's basically it. We're actually not going to do this. If you're in 201, I'd have to show you how to do this. But we're actually going to skip it. I just want you to get the idea of this is how we look at it, right? So the area would be equal to the limit of n as n goes to infinity. I'm going to rewrite the exact same thing because I want the form to be familiar to me for when I use it later. Just distribute the delta x. Right? And in this case, it doesn't matter whether I use right hand, left hand, or midpoint. Right? If I'm using an infinite number of rectangles, they're both going to converge to the same thing. So this thing here has a special name. This is called the integral of the function f of x on the interval ab. It is denoted by this symbol, which was what Nikolai was talking about yesterday. No one knew what the hell he was talking about. Oh, there's like this big squiggly thing, and I was
Yeah, I
like,
know. Oh, Nikolai.
yeah, but there's that big squiggly thing. So it looks like this.
Oh,
Yeah, even the chalk hates it.
And there's an a to the b, and then you write the function f of x
Down.
here, and then write
Put all
the
the
x at the end.
TX.
Right? That is the notation for the integral. So this basically means whenever you see that, it's actually a limit in disguise.
Oh.
It's just the limit of
Oh.
f of x1 times delta x plus blah, 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 all the way down to f of xn times delta x. Right? It's really just a limit in disguise, and it is defined to be the area under the curve f on AB. i.e., integral from a to b of f of x dx is equal to the net area under the curve f of x. Under is in quotations because it's a net area on the interval AB. Right? And so that's the notation that we use for it. So whenever you see that in your book, you can actually interpret it as area, but it has other interpretations that we will get to. Some more terminology, I believe I will.
So if the limit that we are used to finding is like the x plus h minus f of x over a.
That's the definition of the derivative. Here I'm defining the integral. And in particular, this integral, whenever you have the a, b here, it's called the definite integral. So let me actually put that in. You can put the little caret thing in for you. It's called the definite integral. There is such a thing as an indefinite integral, in which case you won't see these numbers here. And I'll explain the difference between the two. But this one is called the definite integral. And what it is, it gives you the area under a curve on some interval that you're considering. So that's the definite integral. Some more terms in this notation, which was invented by Leibniz. F of x is called the integrand. A and B are called the limits of integration. A itself is called the upper limit. Lower limit, sorry, A is on the bottom, it's the lower limit. B is called the upper limit. And the process of computing this guy is called integration. So those are just some terminologies. So from now on you're going to see these, and when you looked at that formula sheet I gave you, on the bottom of that page you saw these squiggly things. This is what it was talking about.
Yeah, the squiggly things, the squiggly thing.
Right. So this thing here, it's really just an S, because you're taking a sum. It's S standing for sum. So you're taking the sum from A to B of all these functions, and you're basically computing a net area. Yep, so and when you actually compute this, if you actually take this limit and get an answer, you said you've done integration. Computing the integral is a process called integration. here I'm just going to mention, note the integral or definite integral gives the net area under the curve. That is, if your curve is above the x-axis, then it will give you a positive area. That would be from A to B. Then computing that would give you a positive area. If your function is below the x-axis, you actually get a negative area. It's going to be the negative of the area between the x-axis and the function. And of course, if you have a function that switches above and below, you combine the two. So if you have a function here that does something like that, that goes between A and B, and let's say you know that the area of this is A1 and the area of this is A2, then the integral from A to B of f of x dx is going to give you A1 minus A2. Right? So the A2, because it's underneath the x-axis, it will give you the negative value of the area. And this can go on indefinitely, right? So you can have a function that looks like that. If this area is A1, that's A2, this is A3, then your integral in this case is actually the value it's going to give you is the area of this minus the area of that plus the area of that. Right? So whenever it's above, it's a positive area. Whenever it's below, it's considered a negative area. Right? Because your rectangles have to go to the curve. So your rectangles are going to give you negative y values. And that's why you get a negative area. Right? If you ever want to find the actual area, you have to figure out where is the function negative, and then you know when you take the integral of that part, you take the negative of that part to get the positive area. Right? So it always has to be considered. Sometimes it's efficient to use geometry to compute the integral from A to B of f of dx. For example, I could ask you the following. Find integral from -1 to 1 of that function. Right. Basically what we have to remember is what function is this? If I say f of x equals 1 minus x squared, what function is that? In other words, that's y is equal to the radical of 1 minus x squared, which means?
Y is equal to 1 minus x squared, all in parentheses, to the power of 1/2.
Sure. There's no difference between that line and this one.
1 minus x?
What?
1 minus x?
No, that's a blasphemy. You can't just read a square root across the sum.
Wait, what do you want us to do to solve that?
Figure out what kind of curve this is, that's what I'm asking.
Oh, it's one of those like, and it starts at a certain point below which you can't go because
Nope.
because you can't have anything less than 0 under the radical.
Square both sides, that's a hint. Now what? It's a circle. Well, in this case, it's a semicircle. It's x squared plus y squared equals 1, right? Which is a circle of radius 1 centered at the origin. But because you have the positive radical, you only have the top half of the circle. Right? So me asking you this is the same as me asking you what's the area here. So what's the answer?
Whatever the area of the circle is, cut it in half.
Right? Which is 1/2 pi r squared. Pi times r squared. So this is literally just pi over 2. So I didn't have to do a sum of functions and take a limit. I can just look at the geometry. I understand that this means area. So if I can draw the function, find the area, right? And sometimes the shape is very nice where you can figure out what the area is. Sometimes the shape isn't very nice and you have to do something else.
That's some really ugly thing.
Yeah, it could be some really ugly thing, or not even something super ugly. It could be something as simple as a parabola, right? X squared, right? Do you know a formula that will compute the area of something that has that shape? No, right? But with integration, we can do it, and we will be able to do it, and we are going to do it. Not exactly right now, though.
Which is the more like back to like doing a shape way or like that? But like what do most like problems usually solve it by?
Almost never this way.
Oh, okay.
I'm just making a general claim. Like, sometimes it's sufficient to do it this way. If you happen to know the shape, if it's something like a rectangle or a triangle or a semicircle, it's no problem, right? You wouldn't go through the trouble of computing something, right? But if the shape isn't nice, where I don't actually know a nice formula, then I wouldn't do it this way. Right? Yeah, that kind of, that ends 5.1.
Are we going to review for the example?
What?
Are we going to review for the example bucket?
Sure, yeah.
No, Jhevon, give us something really ugly.
We don't know enough to do something like that.
Oh.
So I have a question. Is
Like, you won't know how to do something ugly until the end of 5.2.
Okay.
And then you learn a little bit more ugly things in 5.4.
Oh.
Is it always going to be a positive value?
No.
So there's such a thing as a negative area.
Yeah. So if I ask you what is the integral from -1 to 1 of the negative radical 1 minus x squared, then this would be a circle on the bottom. And I'm asking for that area. This will actually give you minus pi over 2.
So it's important not to look at it as like areas of like you said distance like over time couldn't be negative, don't look at it like that. Like kind of look at it as a like,
Yeah, your area can be anything.
just negative.
Yeah, it's net area.
So if integrals are net area, would it be safe to say that the that integral of the positive side of the function plus the same integral of the negative side of negative f(x) would be 0? Because you're
It depends on the function. It depends on if you have the symmetry.
in this case it's a circle. It's that circle right there.
Yeah.
Alright.
Alright. So for what example were you saying?
For literally that one that we just did. If we took the integral of that, the top half, and then we added the integral of the bottom half, that would be 0.
Yeah, but you pretty much you wouldn't end up in a context like that, really. What you're talking about, we actually have to talk about chapter 6, where you talk about area between curves. Like if I actually did a full circle, right? What would happen is you consider this as the top curve, and you consider this as the bottom curve. And your integral would literally give you the area of this minus the area of that. It will give you the area of the circle. You'll actually get pi as the answer, not 0. There's another situation though where if your thing is side by side, not on top of each other, like you can have this function here, right? Right? And let's say that this is exactly symmetric. Then if I take the integral here, I would get 0 as the answer. Yeah. Or if I look at something like y equals x cubed, right? And I go between 1 and -1, the answer is 0. Right? So at this point I could ask you that. In fact, that's true for any odd function. This is one of the reasons why odd functions are nice. Right? So I can tell you something that looks really mean. So I could say something like, x times e to the x squared plus x to the fourth plus 5 minus pi to the e dx. And I could say, what's the answer? 0. Because it's an odd function. I don't have to do anything. If I replace x with negative x, I get the negative of the function. It means that the right side and the left side are exactly the same, except one is negative and the other is positive.
If you say, show your work.
Oh boy.
Well, I wouldn't, it's actually won't be, I wouldn't be able to ask that in this case, because e to the x squared, no, I could ask that for this problem, yeah, which you'd have to do later. But I wouldn't ask you to show your work, because that's just kind of silly. Yeah, but after 5.4, I could ask you to show your work for that, in which case I wouldn't make it that easy for you. I'd put something in there. You have to actually do some work. Because if I make it balanced, there is no work to show. You can just say 0 because it's an odd function, and that's a valid solution. Yeah, I could ask something like that, except for
What? No, I don't get it.
it's not important for you to get it right now, because we are going to do more stuff with this later. We're barely on the surface of integration.
Awesome. I'm pumped up.
Now we're going to talk about something called the fundamental theorem of calculus. Yes, of all of calculus, like calculus.
Let's do
This is the fundamental theorem.
So this is the whole point of this course.
of any calculus course.
Kinda, yeah. The thing is, in 205 we really kind of cover half of this theorem, not the full theorem. It kind of comes in two parts. But we're going to talk about the fundamental theorem of calculus. This is why Newton and Leibniz are known for calculus, because they came up with this theorem. Independently.
In two different locations
Yeah.
at the same time.
Yeah, so the idea is calculus technically has been studied for thousands of years, but it was always separate. There were people who were doing derivatives, and people over here doing integrals, and no one understood that the two were connected. They seem like completely separate. Why would how fast you're moving have anything to do with an area of something? Doesn't make any sense, right? Newton and Leibniz were the first to realize, these are actually two sides of the same coin, right? And the statement is in the fundamental theorem of calculus. And this actually makes the study of calculus a lot easier, because what you're going to realize is that they're actually kind of inverse operations of each other, right? Finding a derivative and finding an area is kind of a reverse process. In other words, if I know a bunch of things about derivatives, I automatically know a bunch of things about integrals. I just flip it, right? And vice versa. So it was a really important theorem, and it's what allows us to, it's what allows calculus to be this useful. Okay, so consider the problem. So let's say f of x is a antiderivative, which I defined last time, of f of x on AB. This you don't really have to know, but I think it's pretty cool, so that I show you. Just gonna run through this. Okay, let's look at this phrase, f of b minus f of a. You know, it's completely arbitrary, but let's consider it. Let's do something even more arbitrary, which you're probably not gonna get. So this is on an integral ab, which I'm kind of thinking as a and b, and I'm going to, again, take a Riemann sum. Right? So I'm dissecting this, call this a x0, my b would be xn. Right? And then here's my x1, x2, x7, right? All the way to xn. So my b is kind of like xn, and my a is going to be x0. And now what I'm going to do is I'm going to add zeros multiple times in a weird way that at first is going to look like, why would you do that? So I'm going to say f of xn minus 1 plus f of xn minus 1 plus well, minus and then plus da da da. I'm going to go all the way down to, this is a minus, f of x1 plus f of x1 minus. Right? So I just add and subtract the same thing all the time. So I'm going to add and subtract f of n minus 1, then I'm going to add and subtract f of n minus 2, add and subtract f of n minus 3, all the way down until I get to x1. Okay. Now what's going to happen is, I'm actually going to start grouping these guys. Group these together. Group them pair by pair. Right, so that f of xn minus f of xn minus 1. Think of that as a pair of numbers together, plus, I'm going to have f of xn minus 1 minus f of xn minus 2 plus, I'm going to continue this pattern. I'm going to end up with f of x1 minus f of x0. Consider that pair of numbers. Now, recall the linear approximation formula. What did that say?
F of x is approximately, it's like the squiggly, it's the squiggly equal, is approximately of f of a plus f prime of a, and then times in parentheses
X minus a, which actually when you think of x minus a, it's just a difference in x values. You can kind of think of that as a delta x. Right? Now, what do we know about f? Big F is what? It's an antiderivative. What does that mean to be an antiderivative? I told you last time.
It's f of a. It's the original.
This means if I take f of x minus f of a, this is approximately equal to f prime of a delta x, right?
Wait, what?
Yeah,
Okay.
you just moved it to the original.
I just moved this to the other side,
Okay.
right? So this would apply to big F, right? So if I apply the linear approximation formula to big F,
Yeah.
that would be true, right? But since big F is an antiderivative of little f, what is big F prime?
Little
It's just going to be little f, right?
All right, one more time.
This means the following. If big F is an antiderivative, it means that f prime equals little f. That's what it means. Right? So saying this is the antiderivative of that means if I differentiate this, I get that. So it means if I differentiate this, I get that. And so if I have a subtraction of big F's, I can actually write it as this.
Oh.
Here, I have a bunch of subtractions of big F. Think of this as the x and the a. Which means now, what's going to happen? You're not going to get 1. This means that f of b minus f of a is, replace each of these guys with f prime, f of xn minus 1 times delta x, right? This is just that. Using that formula, just like plus f of xn minus 2 times delta x plus all the way down to f of x0 times delta x. Does this thing look familiar?
Yeah, we just did something like that.
It's a Riemann sum, right? In fact, it's the left-hand endpoints. Now, take the limit as n goes to infinity of both sides. What's going to happen?
I'm confused. I don't know what.
About what?
My thing is that isn't like, you see how for the approximation formula x minus a is
Yeah.
like your x value that was given to you,
Yeah.
the a value
Mhm.
that was given to you.
Yes.
So That's a change in x.
Yeah, this was like my xn and xn minus 1.
Okay.
So at the end of the day, I'm going to have xn minus 1 times that.
And that the delta x in this formula is the total change in x, not the change in x.
No, the change in the
Those
subintervals.
little intervals
Yeah.
that we just done in one.
We've been doing that as 1, but it doesn't have to.
It could be.
It could be whatever. It's b minus a over n,
Okay.
whatever that is. So now I get this is equal to the limit as n goes to infinity of that. So what's this? If I take the limit as n goes to infinity of this.
You get the area.
It'll
What is this expression? Is it a constant, a variable, a function? It's a constant. It's a function evaluated at some number minus the function evaluated at some other number. It's just a number. What's the limit of a constant?
That same thing.
The constant itself. So this, the left side doesn't become anything different. It's just that guy. Because it's a constant. What is this right side though?
The Riemann sum.
There we go.
It's literally the integral. By definition. That's the definition of the area under the curve.
So this is just to prove stuff. We
That's just to prove that. Yes.
Okay, that's what
This gives us, I think your book calls it part 1, but it was actually part 2. Whatever. Part 1 of fundamental theorem of calculus.
Basically, this theorem states that evaluating evaluating some constant.
Evaluating the antiderivative of a function between two endpoints is the same as computing the area under that function. That's the same thing that we did earlier when I was saying taking the area under the velocity function was exactly the same as evaluating the position function between 2 points. Right? This is just a very more general statement. It means it will work in all situations where you have an antiderivative and a function. So it says here, if f is continuous on AB. Literally this you can forget. This is what you have to remember when I'm writing down now.
So you just confused me.
F is continuous on AB, and big F of x is an antiderivative of f. Then it turns out that the integral from a to b of f of x dx is going to be the antiderivative evaluated at b minus the antiderivative evaluated at a. So to answer the question earlier about what would we do if the function was really ugly, that's what we do. And it turns out that that's actually a lot easier to do than you think. Well, in total 5. Integration gets really, really hard. Like differentiation is like the very young little brother who doesn't give any trouble. Integration is that wild teenager that you can't control and things can really get messy. Right. But that's called the fundamental theorem of calculus. You have to know that theorem. And you have to know how it's going to be applied, which basically we're going to be able to find antiderivative of things. I'm not going to go much further. With this in mind, also note, and I gave you examples of this last time, there's a theorem that says f of x is the antiderivative little f of x, then the most general antiderivative is f of x plus c, where c is an arbitrary constant. Right? The idea is if I differentiate a constant, it would go to 0 and it won't matter, right? So that's why something like x squared plus 5, or x squared plus 7, or x squared plus pi, or x squared plus e, x squared plus anything is the antiderivative of 2x, right? I can add an arbitrary c here and it won't change the answer.
How do we actually find this c?
You need more information.
Alright.
So I could say something like, find the antiderivative of 2x where when x equals 0, it gives you a value of 4.
Oh.
And then I'd be able to find the c. So I would find the antiderivative, I know it would be x squared plus c, then I plug in x equals 0 and set it equal to 4, and I can get c equals 4. So I know the particular guy I was looking for was x squared plus 4. Right, but other than that, you always just write a plus c, you don't actually know what the answer is. Unless you're given more information.
Does it matter if you're writing in uppercase or lowercase?
Uppercase is technically it doesn't matter, but it's really weird to write lowercase. You use lowercase c for that. So for example, to go back on examples from last class. I can say that the antiderivative of 2x is x squared plus c, right? This says the antiderivative, which is really an integral, which is what the fundamental theorem of calculus tells us. The integral is an antiderivative. Antiderivative of 2x is x squared plus c. Means all functions of this form, when I differentiate them, I get this function.
Professor,
Yes?
I feel as though like the only reason we know the antiderivative of 2x being x squared plus c is kind of like we kind of already know the answer, x squared. But like if it was some weird function that we didn't know the antiderivative, like we've never differentiated some other function to get our original starting function, like how does that happen?
The rules on the bottom half of the page that I told you. It's basically going to be the short answer. Right? There are formulas that's going to tell us how to find the antiderivative of some basic function. And so in this class, you're going to be able to find the antiderivative of any polynomial, any exponential, well, some exponentials if they behave nicely. Exponentials can get kind of weird. So not every function actually has an antiderivative. That's going to be one thing that you're going to notice. That's one way in which integrals can be way complicated. Because yeah, you look at a function like e to the x squared, find the derivative. No problem. Find the antiderivative. Doesn't exist. It's impossible to find a function that when you differentiate, you get that function. Right? So there are little nuances here that you have to watch out for. Integrals can get really messy. For now, we'd stop there. Yeah, so in the next class after the test, I'm actually going to show you how to compute integrals for different functions. So you're going to be able to find the integral of x squared plus 1 dx. And so, by the way, if I said something like this, what would that be interpreted as?
The area under the curve of x squared plus 1 between the 0 and 1.
Right, so if I had x squared plus 1 and asked you, what is the area between 0 and 1, you'd literally do this computation, right? Which was the one that we actually did? We did between 1 and 5, was it? Mm-hmm. Of x squared plus 1? Right, and we approximated the area, right? We did the right hand with 4 rectangles. It gave us like 58 or something, if I remember. Yeah. Then we did the left hand with 4 rectangles and it gave us 24? 34? Right. And so you might ask, what is actually the area? Turns out that's actually the area. And next time we're going to realize that the antiderivative of x squared is actually x cubed over 3. Right? Notice that if you differentiate this, you get that. The antiderivative of 1 is x. Differentiate x, you get 1. And what you're going to do, according to the fundamental theorem, what are you going to do?
Plug in 5. And
You're going to plug in 5. You're going to take f of the upper limit, 5 cubed over 3 plus 5, which is like big F of 5, minus, plug in the lower limit, 1 cubed over 3 plus 1, which is big F of 1. And when you subtract those, that's the actual area. So if you want to know how close you are to the actual area, compute that and it'll tell you. Right? And you'll notice it has to be less than 58 or whatever, and greater than 34. It's somewhere between. But we'll stop right there. If you didn't understand any of this, don't worry about it. We are going to go over this in detail. I'm just throwing some ideas out there. But yeah, and in the same way that derivatives have a lot of interpretations, it's not just how fast something is moving, even though you can think of it that way, but you can think of a derivative as being able to find the speed of something, or to find related rates or optimization. You can use them for a bunch of things. Integrals in the same way can be used for a bunch of things. It's not always just straightforward area. It can have interpretations in different contexts. That being said, I will now take questions on what you've been studying from the review. Any problems you want to go over? And we'll pick up with this after the test.
Kind of give us optimization.
Optimization? Yeah?
Last question, the brownie points. You asked us to do it on our own.
Yeah.
Can you go over it?
The brownie point, that's let's see. Well, you guys were supposed to go over it on your own, though.
That was really
Yeah, so we need it all.
Okay, so tell me what you did. Did you guys actually try it?
See, I always sit on curve stuff.
Okay. But did you guys actually try it? What did you try for that? Yeah, so this was actually on a final. It's actually harder than a problem that I would ask, but it was on a final back in 2009. It says, a travel agency offers a boat tour of several Caribbean islands for 3 days and 2 nights. Irrelevant. You throw away that information. It's not useful to you. For a group of 12 people, the cost per person is $800. For each additional person, above the 12-person minimum. So 12 people are the minimum they'll book the cruise for thing. But for each person above 12, they reduce the cost by $20 for each person, right? So if you have 13 people, each person would pay $780, right? And if you have 14 people, each person would pay $760, and so on and so forth. The maximum group size is 25. What tour group size produces the greatest revenue for the travel agency, right? That is the problem, right? So you own this travel agency and you're doing this promotion, right? 12 people, $800 per person. But the more friends you get to come along with you, I'm going to reduce your price by $20, right? What is the best size tour to book? Is it just the maximum 25? Would that give you the best? Would that make you the most money? Are you guys just saying that? Yeah, well, that would be too obvious. Obviously, that's not it, because you can't trust Jhevon. It's not my problem, so it could be. That could be 25. Could be the best. So, what do we want to do here? So, 1, you read the problem. We just read the problem. 2, if possible or necessary, you draw a diagram. I don't really see a diagram that would be useful here. So, diagram I don't think would be helpful here. So, jump to step 3. Can you think of a constraint and an objective? Now this one takes a bit more thought than all the other problems. Like if you're the travel agency, what would your objective be? Let's start there.
Make more money.
To make money. It's you, you're traveling. What would that mean?
To maximize. How
Maximize what?
amount of profit you get out of all that.
Maximize profit, right? In this case though, we are given no information about how much it costs me to run this travel agency. So maximize profit just becomes maximize revenue. Right? And what is revenue? X times the price that I'm charging. Okay. Now our objective is to maximize this function, right? So give me this function. So x is just x. X is going to be the number of people. You may want to write that as x. And the price is going to be the cost per person. Right? Now figuring that out is going to be the challenge here. What is the cost per person as a function? Give me a function that describes the price.
Each person is 800,
Huh?
Each person is 800.
Not always.
So 800 minus.
Up to 12 people, it's 800 per
Right,
person.
it's 800 plus 800 plus 1 person. We did it before.
So it is 800.
It's the like finding the 101 person thing. I can't remember right now.
Let's define our x though.
What is it, 100 plus 199 plus 2?
Let's actually define our variables. Make it easier on us. Let x equal, what do I want x to be?
Number of people.
I probably wouldn't make x the number of people. Because directly speaking, it's not going to be. I think it's going to be hard to set things up like that. Remember we have a minimum and a maximum number of people, right? So I'd probably say something like, let x be the number of people over the 12 person minimum. Right? So if I were to say cost per person, what would that look like? 800 for each people up to 12, but x is the number of extras. So what would that look like?
X.
So it's already
It has to be 1 and 3.
You're subtracting something. You're subtracting what?
20 discount for each.
$20 for each person, right? So what would I subtract?
28.
20x. X is the number of people above 12. For each one of those persons, I'm going to subtract $20. This will be the cost that each person will pay. So what is the number of people? X is the number above 12, so in total, how many people will I have on the boat?
X plus 12.
X plus 12. Right? Therefore, how much money will I make? I have X plus 12 people, each of them are paying this much. How much money am I making?
Multiply them.
X plus 12 times 800 minus 2x, 20x. And now maximize that. After that, find the derivative, say equal to 0, find the critical point, find the maximum. Your constraint is kind of just the fact that your x has to be between 12 and 25, right? So if your maximum revenue happens beyond 25, then 25 would have to be the answer, right? Or vice versa. So you have to keep that constraint in mind. Your x cannot go everywhere. So you're only considering the biggest value on the interval. Our x is the people above 12, so it can go from 0 up to 13. Right, so you have to have a number between 0, x has to be between 0 and 13. So you're going to find the largest value that this function attains on that interval. You're going to find the absolute maximum on that interval. But yeah, I thought coming up with this kind of function is kind of complicated. It's not something to put on a test. contrary to popular belief. I put problems that look scary. They're not actually scary.
They are
To you.
scary.
It's all in your head. Okay, other problems. And of course, you can differentiate this. You could use the product rule if you want, but I'd probably just multiply out and do the power rule, and then find the maximum. It'll be a quadratic, so you don't even really need calculus, right? You just multiply it out, find the vertex of the problem, and see if it falls within this range.
It falls outside of it.
If it falls outside, then you would say I have to go to the most.
So the 13 is the answer.
So 13 would be the answer, which would mean 25 people would be the best, right? So because your function would would be an upside down problem, right? So look like that, right? So this is at 0 and 13, and oh, you said the maximum falls outside?
Yeah.
Did you check it? Okay, so you would have a situation like this.
14.
It would look like this. So here's where the vertex happens, but 13 happened before that, right? So what's the most money I can make? Well, it's going to be at the very edge. So it means I need 13 extra people. So 25 would be the best to book it for. If this vertex happened before, then it would be some number less than 13, which is what we have to look for. Yeah, but the calculus will tell you. You need to find the absolute max or min on 0 to 13.
And only if it's in that interval can you use it. So like you were saying, just because the vertex was outside of it. Like,
Yeah, that means the critical point isn't in your interval, so the absolute max would be either one of the endpoints. In which case it would be the 13. Okay. Other problems?
Yes, I have like 3. So,
Okay.
the first one is it's a related rates problem.
Okay.
The length of a rectangle is increasing at a rate of 8 centimeters per second.
Okay, hold on. So I have a rectangle.
Yes.
Call this the length and the width. And I know the length of a rectangle is increasing at
8 centimeters per second.
Mhm.
And its width is increasing at a rate of 3 centimeters per second. When the length is 20 centimeters and the width is 10 centimeters, how fast is the area of the rectangle increasing?
10, and which is 10, right?
Yeah,
Right, so that's the question.
yeah. I don't know.
So we read the problem, which you read it for me, thank you very much. I drew a diagram, which was going to be step 2. I'm going to label the diagram, anything that's changing with a variable. It says here that both the length and the width are changing, so length and width are labeled a variable. These are the rates, so this is what I know, and this is what I want to find. Which brings me to, that was step 3 or 4, whatever. And so now what am I going to do? Find an equation that relates all of them, right? What would the equation be here? I have L, W, and A. Can I find an equation that relates L, W, and A?
I was thinking the area of the rectangle. So
Yeah.
give A,
Would be
X times, L times W.
LW, right. Now you're going to differentiate
So you have dA over dt
dA dt.
is equal to dr over dt times dw over dt.
No.
2 times 8.
No.
Oh.
You need a product rule. There are 2 functions here. L is a function of t and W is a function of t. They're changing with respect to time. So I differentiate the L, leave the W alone, plus leave the L alone, differentiate the W.
dw over dt.
Which means that my dA dt, I don't need to solve for anything here. They gave me all the numbers. My dL dt is 8. My width, did it say 10 or 20?
10.
My width is 10, plus my L is 20, and my dW dt is 3. And so that's going to be the answer.
Okay,
So
so,
it'll be that much centimeters squared per second, whatever the variable is.
okay. The next one,
What final was that from?
that was, I think you just, it was a random one. It's from the more examples on the related rates sheet.
Oh.
Number 2.
For more examples.
Yeah.
So it wasn't on a final?
No. So you just put
Okay.
it.
More examples. Number.
Number 2.
More examples. number 2. I feel like there was a final problem that was very similar to this. Okay.
Then for exponential growth,
Yep. Is this on a handout or a final?
it's on a handout
Okay.
from spring 2010.
So it was from a final. So spring
Okay.
2010,
I mean, whatever. Yeah.
problem what?
Problem 4.
Okay.
Let P of T be the population of a colony of bacteria.
The PFT is a population. Okay.
At 1 p.m. there are 50 bacteria,
Yeah.
and at 3 p.m. there are 350. Assume exponential growth.
Yep.
Find the differential equation satisfied by P of T.
Is that part A or?
Yeah, that's right.
So part A asks for differential equation.
Yeah,
Okay.
so I'm confused on what to do there. That's like P
Just
prime
differential
equals-
equation. P prime equals RP, but you have to find the R value.
Okay.
How are you going to find the R value? ln2 over what?
Whatever the half-life is, whatever the decay rate is.
I don't recall her telling me what a half-life was.
There is no
We
half-life.
do
They didn't tell me the
just
half-life.
do P equals E to
You know that that's the
P
equation that
zero
covers
P
it.
RT.
And so now,
And then you put the time.
I call this the initial time, right? That's the first time. And I call that t equals 0. And this is where t equals 2.
And then T would be 3.
So I know that I have 50 bacteria when t equals 0. This would mean that P naught is 50. And so then this means I have P is equal to 50 e to the RT. And then I apply the second one. I know it's 350 when T is equal to 2. In which case now I'm just going to solve for the R. So I'm going to have 350 over 50, which is 7, right?
Yeah.
Equals e to the 2r. How do I solve for r? ln both sides, I get ln7 equals 2r. And this means that r equals ln 7 over 2. And so I come back here and I say p prime is equal to ln of 7 over 2 p. That's your answer. I'm tense because you guys are freaking out. You need to find your zen.
Then I have a curve sketching.
So that was it, part 8. There's
There's more, but I don't need help for it. Should we do the whole thing?
Yeah, we should do the whole thing.
Okay. B is find P of T and simplify.
oh well, we just did that here. So B, in order to get the answer for A, I had to find P naught and I had to find R. So now I'm just going to plug them in. P equals 50. E to my R was ln 7 over 2 times T. I'd leave it there. You could actually simplify it more, but I think that's fine.
Okay. And C is what is the size of the population at 6 p.m.?
Right, so basically I want P is this when T equals 5, right? Because I've started to measure at 1 p.m., 6 p.m. is 5 hours later, so this just means I want P of 5. Just plug in 5 for the T.
So when you use the ln2 or r when you give you an outline?
Yes.
Is that it? That's.
Can I leave
you
it
have to take
away?
that further?
Thank you. D is when will the population reach 1600?
Okay, so here I know that my P is 1600, and I want to figure out T, right? Because they said when, right? It means they're looking for a time. So I'm going to plug in 1600 equals 50 e to the ln 7 over 2 t, and I want to solve for T. So divide by 50 equals e to the ln of 7 over 2t.
32.
5 goes into what?
32 is the answer.
32. And so now what?
ln.
Right, the t is in the power, so I take logs to get that power down. So this is ln of 32 is equal to ln of 7 over 2t, which means my t is going to be 2 ln 32 over ln 7.
Wait. Okay, this is where I messed up. I got ln 32.
I multiply by the 2. and then divide by ln of 7.
Can I do ln 32 over 3.5 is equal to t?
ln 32 over 3.5. How did you get 3.5?
Oh wait.
Oh, no, that's not true. Be careful, it's not ln of 7 over 2. It's ln of 7 over 2. You can't divide that 2 into a 7, so be careful. You can't bring things inside an ln, right? Think of the ln, it's a fortress. Like if you're in there, the only way to get you out is to do an exponential. You can't infiltrate so-called.
Yeah.
Yeah, so they're not the same thing. They're different, very different numbers.
Okay. The next one is a curve sketching.
Okay, that's going to take forever. Is that from a final?
From a. Oh, so much going on. Is it called? It's a handout. Hold on. And it's the one that you gave us the first derivative, second derivative.
Okay.
Um.
It's from the handout again?
Yeah.
So all of those I think I took from finals anyway.
Yeah.
But although I'm not
I
sure
chose B.
it was your final. I thought B I actually did. Didn't I do B?
You did.
I did do B.
Well, I have questions.
I think the only one I didn't do was C. Yeah, but what's your question?
Okay. Well, my main two questions are for finding the min and max. Like, you're supposed to set the second derivative equal to 0?
No.
Okay.
Max
let's
is
just do-
saying the
can we
first
just-
derivative equal to 0. If you want to talk about increasing, decreasing maximums or minimums, the first derivative is what you're looking at.
I mean, did I say first? I meant second. Okay. So I need help with that little graph that you do. After you set your min and max and you choose a point in between
Yeah.
to find out if it's increasing or decreasing. So can we just do C?
So we're doing C, not
Yeah.
B.
Not B. Yeah.
Okay. So f of x equals x squared minus 9 over x minus 1 squared. Yes.
Yeah.
This is 2 times 9 minus x over x minus 1 cubed. And my f double prime was 4 times x minus 13 over x minus 1 to the fourth. Okay, so we're going to run through the steps. They never really ask us for a domain, but it's obvious here it's everything except x equals 1. So let's move on. So the first thing we're going to want to find are intercepts. So let's talk about the x-intercept. How do I find x-intercept? Set y equals 0, which is x squared minus 9 over x minus 1 squared. This means x squared minus 9 is 0, which means x is plus or minus 3. Y-intercept. That means x equals 0, which means your y is going to be 0 minus 9 over 0 minus 1 squared. So it's minus 9 is the y-intercept. Then I'm going to talk about asymptotes. What about the horizontal? I'm going to take the limit as x approaches infinity of the function, and the limit as x approaches minus infinity of the function. What's the answer in the first case?
You forgot about the denominator, right? No. 0.
1 and 1.
Is it because of the ratio?
Yes, the highest power on the top and bottom is x squared. They're the same. So if I were to multiply this out, it would be x squared minus 2x plus 1. This is the highest power, that's the highest power, so there's a 1 in front of this guy, there's a 1 in front of that guy, so it's just 1 over 1. Vertical asymptote
Set the denominator to 0.
is where the denominator is 0. This means that x minus 1 squared equals 0, which means that x equals 1 is the vertical asymptote. And this means that y equals 1 is the horizontal asymptote. Now we're going to talk about increasing, decreasing, maximum, minimum.
I have a question.
Yes.
Why on the handout did you write you must for vertical asymptotes you must find a number such that the limit as x approaches like a from the right from the left.
Mm-hmm.
But then we just set it equal to 0.
Yeah, if you continue reading, I explained. I said in the case of a rational function, this will always be where the denominator is 0. Right. So curve sketching, you can do it for anything, right? But there are things that don't have denominators that have asymptotes, such as a log. Right? So if I'm looking at ln x, there's no denominator to set to 0. So you go by the basic definition of what I put there. So the what I put there about the limits going to infinity, that's just talking about the general definition. So if I look at the log and I take the limit as x approaches 0, notice that my function swoops down to negative infinity. So I know that 0 is the vertical asymptote. But with rational functions, we know that this always happens when the denominator is 0. It's just a coincidence with rational functions. So for rational functions, I don't think of that definition. It's kind of harder to work with. I think of set the denominator equals 0. It's going to give you the values that you go to infinity or negative infinity. So yeah. So increasing, decreasing max and min means we're using the first derivative. So I'm going to set the first derivative equal to 0 or undefined. Right? So the first derivative is undefined where?
When x equals to 1.
Right. It's divided by x minus 1. So x equals to 1 is a critical point. Where is the first derivative equal to 0? When x equals 9, how do you know that?
Set the numerator equal to 0.
Set the numerator equal to 0. The only way for a fraction to be 0 is if the top is 0. So you divide both sides by 2, and then you just get x equals 9. So I have two critical points here, 1 and 9. And so now I'm going to plug in numbers in between them. So I can plug in like a 0 here, a 2 here, a 10 here. 0 I already actually plugged in. It gives me a negative, so I'm now decreasing. If I plug in 2 into the derivative, remember you're always plugging in here. On the top, I get a positive number. On the bottom, I also get a positive number. So that's positive, increasing. If I look at 10 into the derivative, I have 9 minus 10, which is negative. 10 minus 1 is positive, so I have a negative divided by a positive, so that's negative. And so that's decreasing. Do you have any max and mins here?
1 is a minimum and 9 is a maximum.
No. No.
Oh, because
Wait,
x
1
is
and 9
the
will make it 0.
You're undefined at 1. Your function doesn't exist at 1. 1 is nothing. 9 is a maximum. So then if I look for increasing, I'm increasing on 1 to 9. If I look for decreasing, I'm decreasing from negative infinity up to 1, union 9 to infinity. And I have a maximum at,
We just plug it back into
I have to plug it back into the function, at 9 comma 9 squared minus 9 over 9 minus 1 squared. Now I move on to the next category, concavity and inflections. Right, so you always do intercepts, asymptotes, increasing, decreasing, max and min, then you do concavity and inflections. So I'm going to look for concave up, concave down, and any inflection points that happen. In this case, I look at the second derivative where it's 0 or undefined. Where is it undefined? Where denominator is 0, which is x equals 1. Where is it 0? Where the top is 0, which is x equals 13. So now I'm going to test this interval between 1 and 13, and I'm going to test that on the second derivative. Right? Remember, in this one, I tested the first derivative. So again, plug in a number like a 0. Here I plug in a number like a 2. Here, 14. So I plug in 0, and I plug it into the second derivative. So I plug in 0, Notice that the denominator here is a fourth power, so the denominator is always going to be positive, so I just look at the top. Plug in 0, I get a negative.
Concave down like a frown.
Plug in 2, I get a negative again. And plug in 14, I get a positive. And yes, concave down like a frown,
So 13 will be
down like a frown,
Up like a
up
cup.
like a cup. Where's inflection?
13.
13 is an inflection. 1 also, right?
No,
No.
it doesn't.
It doesn't even change sign, and it doesn't exist. Even if it did change sign, it would still be nothing, right? There's an asymptote here. We found that. And so now I can talk about concavity. So now I know I'm concave up on 13 to infinity, and concave down negative infinity to 1, meaning 1, 2, 13. And my inflection will occur at 13, comma 13 squared minus 9 over 13 minus 1 squared.
Would you want us to do the math out for that or no?
Probably not. Okay, so now we actually have enough to draw the graph. Start putting things in. Start with the first category and move onwards, right? So you start with intercepts. Where are intercepts?
Plus and minus 3.
Plus and minus 3, where are the x-intercepts?
And negative 9 will be y.
Negative 9. Okay.
And asymptotes were horizontal was 1.
Okay, so we have a horizontal asymptote. 1. Vertical asymptote is also at 1. Now in the bottom we're going to put our increasing and concavity results. Oh, we still have more coordinates to put in. Let's put in these guys first. Where were we increasing? From 1 to what? Right, we'll try to use a better scale here then. Because I think we have to go up to 13. Okay, so let me put 1 a lot closer here. Like a 1, 3, a 9, 13. So I'm increasing from 1 to 9. And I'm decreasing everywhere else?
Yeah.
Minus 3. Okay, what about concavity? Concave down from 1 all the way back, concave down,
And 13.
and up to 13, still concave down, and then I'm concave up here.
We got the vertical asymptote.
I have to put back the vertical asymptote. Okay. Now, do we have points?
Yeah, inflection.
Where was the maximum? It was at 9 comma what?
9 comma
Whatever you put in.
the 72.
It was like 9 squared minus 9 over
Over 64.
64. Right, which is definitely bigger than 1, right? So I don't really care where that is. I know that's right here. And that was a maximum. So this is a maximum. It's at 9 comma 9 squared minus 9 over 64. Okay. There was no min. Did we have an inflection?
Yeah.
At 13, what?
13 squared minus 9 over 13 minus 1 squared.
Okay. So 13 squared is like 169, 12 squared is 144. It's still slightly bigger than 1, right? So 13.9 or 12 squared. Okay, now let's draw a picture. That's all the information we have. Now we forget about all this and we're only looking here. So I need to be decreasing concave down, and I need to pass through this point and that point. Right, so I'm going to be like, concave down means down like a frown. So I'm so far so good. I know I don't go above this line, because if I pass this line to come back and level off, I create a maximum. And I know I only have one maximum. So I know I have to stay below this line. And I would need an inflection point. So I know my graph has to look like that. It settles at 1 as I go to infinity, but it keeps decreasing concave down. So that's that side. What about this side?
Then you
Increasing concave up. I pass through that 3 and hit a maximum here. That's concave down, like a frown. Once I pass this maximum, I'm now in the decreasing range. So I decrease, but I'm still in the concave down region until I hit this guy.
And then you're concave up.
And then I'm concave up,
Decreasing.
decreasing. So I actually level off at that one. How do I know I couldn't go down here or down further? Right, there's an asymptote. Why can I pass the asymptote and then come back?
that would create another.
That would create a minimum. So I know I don't do that. I stay on top of it. Yep, that's the graph. So it's going to be this way.
We got this.
If you go a little math right, because your graph's a little wrong. How many points is that?
Well, if you got the math right, it would be very weird.
That's
for
how
graph.
it's wrong. If you're specimen even trash.
I don't know. Case by case basis. Yeah. What?